Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So today we will be solving the problem sliding window maximum from the SD sheet. So what does the problem state? The problem basically states you'll be given an integer array, okay, and you'll be given a size k equal to 3, and you need to figure out what is the maximum in all the subarrays of size 3. Now for an example, if I consider the first subarray of size 3, that is this one. Now in this, which is the maximum? 3, so you take 3. If you consider the next subarray, that is this over here, which is the maximum, again 3, so you take 3. In the next subarray, which is this one, which is the maximum, definitely 5, so you take 5. So what you have to do is, in every subarray of size 3, you need to print the maximums in it. That is what the problem states. Now if this question comes up in an interview, what is the first solution that you're going to give to the interviewer? It should be the naive solution. What you're going to say is, since you know, first subarray starts from the 0th index, the second subarray starts from the first index, the third subarray starts from the second index, and so on. The last subarray of size 3, I'm talking about size 3, starts from the 5th index. So what if from 0 to 2 I can traverse? What if I can traverse from 1 to 3? What if I can traverse from 2 to 4? What if I can traverse from 3 to 5? From 4 to 6, 5 to 7. If I can traverse through and all the subarrays of size 3, and in every subarray, if I can figure out the maximum, I think this can be a possible starting solution that you can give to the interviewer. So, how will the code structure look like? Now, can I say I will easily traverse from 0 to 5? Indeed. And I know the first subarray is from 0 to 2. So I can simply traverse from that I to I plus k minus 1. Why? Because 0 plus k is the size 3. So k minus 1. 0 to 2 is the first subarray. The next subarray is from 1 to 3. While the next subarray is from 2 to 4. And similarly, I can go on. So if I write this nested loop, I can definitely find out the maximum of every window of size 3. And what will be the complexity? I can say this loop is near about n, like near about, and the inner loop is around k times. So it's a nested loop of n into k, which is almost an quadratic solution. So obviously the interviewer will not be happy with this, and he'll ask you to optimize this solution. Before moving on to the next part of the video, let me tell you about Coding Ninjas. Now, Coding Ninjas is one of the largest coding education company, and they have taught around 50k plus students. Now, they offer you courses in programming in different languages like C++, Java, Python. They also have courses for machine learning, Android development, data science, and web dev. The content quality is exceptional as it is made by experts from IIT, Stanford, Amazon, and Facebook. They do offer you 1:1 doubt resolving support, and the average doubt solving time that they take is literally the best in the market. Now, since the courses are really well structured and so many have benefited from it, I guess you should give it a try. And if you feel so, do use the link in the description too. In order to optimize the brute force, that is the BIGO of n into k solution, to a much more optimal solution, we're going to use the concept that we used in NGE, that is the next greater element. If you remember, we used the concept of storing elements in an increasing fashion. So over here, we are going to store elements in a decreasing fashion. And in order to do so, we will be requiring something which is known as deque. Now, what is a deque? Deque is nothing but a doubly linked list that is being implemented at the backside. Now, what is a doubly linked list? A doubly linked list does allow you to push at front, right? It will allow you to push at front. It will always allow you to pop front, that is, you can take out anything from the front. Also, it will allow you to push back. Also, it will allow you to pop back. So this is what a deque is. It allows you operations on both the sides. Now, in order to solve this problem, what you'll do is you'll start iterating. Okay, so you'll start iterating at the 0th index. And what is the value at the 0th index? That's 1. Now, does your deque have anything? So I see that our deque doesn't have anything. So in order to maintain the decreasing order, you can simply push back this value 0. So I'll just push back this value 0, which is the index. Okay. Now let's move to the next, which is the index 1. So since you have pushed back the value 0, that's nothing but the value 1. Correct? That's nothing but the value 1. Now, the moment you come to the index 1, you have a value 3. Now, logically think. if you have an array element which is 3, right, and you're looking for the subarray maximum in a window of size 3. So if you've got someone as 3, just realize if you've got someone as 3, will storing this one matter? Will storing this one matter? Definitely not. Definitely not. So what you'll do is you'll start checking from the back, which is the back element, 0th index, that's 1. So I see that 1 is lesser than 3. Yes, I see that 1 is lesser than 3. So I do not require 1 anymore because I've got 3, which can be my answer now. So what I'll do is I will take this out. Yes, I'll take this out. And after this, the deque is empty. So I'll take this index and I'll plug it to the back of the deque, right? After that, I'll move to the second index. Perfect. So since I've moved to the second index, what value do I have? I have a -1. Remember, your deque has this first index, which is nothing but the value 3. Now, as of now, I have a -1. Now, this -1, if I plug in into my deque, it will maintain a decreasing order. And I know if I get a -1, it's not the maximum because 3 will be my maximum. So no need to remove anything. Rather push this index to the back of your deque. Pushed. Now, here comes the main point. Can I say 2 is the last index of the first subarray of size 3? Yes, I can. So what I'll do is, since I'm storing in a decreasing order, can I say if I look from the front, whatever value is at the front, that is the first index, the value is 3. Can I say for this particular subarray, the maximum I'll easily get at 3. I'll easily get it as 3, indeed, right? Right after that, I'll start moving to the next index. So the moment I move to the next index, what's the value? That's -3, correct? So will you remove anything from the deque? So just imagine if you plug in a -3, will the decreasing fashion be maintained? Indeed, because 3 is greater than -1, -1 is greater than -3. So the decreasing is maintained. So what you'll do is you'll take this third index and you'll push back to the deque, right? So since you've pushed it back to the deque, now the next step is, since you are the third index, you have one more subarray of size 3 which is ending at the third index. So I need a maximum for that. Since I'm storing in a decreasing order, I'll look from the front and I'll see the index 1. So what is at the index 1? 3. So I can say 3 is my maximum for the subarray of size 3 now. Perfect. Now I will move to this fourth index. This is the point you need to understand something. So if you move to this index 4, can I say I'm just concerned about this window? I'm just concerned about this window of size 3. Correct? So what is over here? That's the index 1. Shall I store that in my deque? Shall I store that in my deque? And the answer to that is no, because my boundary is only this much. And I'm storing an index which is outside my boundary. So if at any moment I store something outside of the boundary, I'll check from push of front. I'll check from front. I will check from front, and if I find anything out of boundary, I'll simply pop it up. So I pop that front, right? After that, since I popped it, now I am at an element 5. I'm at an element 5. Now tell me, if you have got 5, does -1, -3 matter? Definitely not. They don't matter to you anymore. So what you will do is, at first, you'll remove the smallest. So what is third index? That's a -3. Is that smaller than 5? Yes. So you'll remove it. So you'll check from the back. Next, smallest is the second index. That's -1. Is -1 smaller than 5? Indeed. So I can also find this smaller. So I'll remove it. So once you have removed everything that is smaller than 5, right? So once you've removed everything that is smaller than 5, right? Just push in this index 4. So you've pushed in this index 4. Now, since you've removed these guys, again the new order will start from 5. Now as of now, you are currently at this. So this is your subarray of size 3 now, right? And if you look from the front, the index is 4 and that is corresponding to a value 5. So this will become your maximum of the new size 3 sliding window. Perfect. Now it's time to move to the fifth index. Again, what is at the fifth index? 3. So if I talk about the new window, can I say this is my new window? Do you have anything that is out of boundary in your deque? No, we do not have anything that is out of boundary. So what we will do is, yes, what we will do is, we will simply take 3 and see, is there anything lesser than 3? No, there is nothing lesser than 3, because if you have got 3, all the lesser elements will no more matter to you. But since there are nothing lesser than 3, I'll just insert it to the deque. So I'll insert it to my deque. Now currently I'm standing at 5. Now I know this is my subarray that I'm concerned about. So can I say, if I look from the front, the index 4, if I look from the front, the index 4 is having a value 5, which will definitely become my maximum of this subarray of size 3. Perfect. Now it's time to move to this guy, right? At the moment I move to this guy, this corresponds to this, the index 4 to 6. Do you have anything in the deque that is out of boundary? No, we do not have. But we have elements that are lesser than 6. So first element that is lesser than 6 is 3. So just take it off. So you have taken it off. Make sure you check from back, right? Because it's a decreasing order. Next, check 5. So you'll take this off. Taken off. Correct? By the way, this is just for representation. So you have taken everything that is lesser than 6 because they won't matter. They won't matter because 6 is greater that you have got. So anything lesser than 6 will no more matter now. So you have removed that. Now take the index 6 and plug it into your deque. Correct? Now it's time to find the maximum of this subarray. So if you check out from the front, it's the index 6 itself, which is corresponding to a value 6. So now your deque has the index 6, which corresponds to a value 6. Perfect. Now it's time to come to the index 7. At the moment you come to this index 7, you look across this. This is your boundary, correct? Does your deque have anything which is before the index 5? No, it doesn't have. So it's time to remove anything that is lesser than 7. So this guy is lesser than 7, so you'll remove it, correct? Now, once it is removed, take this index 7 and plug it in. So you have done that, correct? Now it's time to check from the front, which is the index. So you have a 7. You have a 7 which corresponds to a value 7. So this 7 becomes your maximum of this last subarray. So once you've done this, the iteration will be over and you'll move ahead. So once you move ahead, can I say all the answers that you got will be the maximum for all the sliding windows of size 3. Indeed, that will be. So let's discuss the intuition. The intuition behind storing the decreasing order is very simple, because at any moment, if you reach any index a of I or any element a of I, can I say anything lesser than equal to that, any element lesser than equal to that appeared before can no more be your maximum, because you have got someone which is greater than that, which is greater than equal to that. So this guy will be my new maximum. So anything lesser than that has to be removed, and that is why I've stored in a decreasing fashion, so that I can remove, I can go on removing from the back. So that is the entire intuition that I am following. So if I ask you what will be the time complexity, the time complexity will be nothing but big O of n plus big O of n, which is near about big O of n. I'll ask why big O of n plus big O of n? Because see, you are doing big O of n iterations, that is, you're iterating for every index. Now tell me, when you're removing elements, because the moment you reach a of I, the first thing that you're removing is all the out of bound index. Perfect, you're always removing all the out of bound. Basically, if your subarray is some like this, you're removing anything that was before this 4, correct? So out of bound you're removing, and also you're removing anything that is lesser than equal to a of I, because they no more matter now. So can you tell me in total, when you move from here to here, how many elements will you remove in total? You'll be like, that's n elements, because at max, throughout the iteration, I repeat, throughout the iteration, you will be removing, probably for the first time you remove 2 elements, next time you'll remove 1 element. So in total, you end up removing n elements, because in an array, at max there are n elements. So throughout the iteration, you'll remove n elements. So that's why the complexity is n plus n amortized, right? And what is the space complexity that you'll be using? Definitely big O of k. If you remember, since you are throwing out all the out of bound indexes, so at max, the deque will only store the size of the sliding window, that is k. At max, it will store k elements. So the external space that you're using is big O of k. And this is the most optimal solution that you can get for this problem. Now it's time to discuss the C++ as well as the Java solution to this problem. So if you check out the C++ solution, you're given the nums array, correct? as well as you are given the size k. So just quickly you'll declare the deque. Again, you can implement the doubly linked list, but yeah, you can use the deque stl. You can also declare the vector. Now what we initially did was we iterated through from 0 to nums.size. If you remember, we started from 0 and we kept on iterating till 7. So that is what we have done. Now the first thing, this is nothing but all the out of bound will be removed. Out of bound will be removed. Remember this. So you just need to check if your deque is empty. Correct? You have checked if your deque is empty. And from this front, if you remember your deque was something like this. From this front, you check the front element. Is that equivalent to I minus k? Why? So why are you checking just for I minus k? Imagine you're standing at I. So this is your subarray, right? So the length is nothing but k. So this guy will be the out of bound guy that will be in deque. So I minus k is this element, So you just check if this element is I minus k. If that is, you just say, hey, can you just go out? That is pop front. Once you have done that, what you'll check is, again, you'll keep on iterating till the deque is not empty. And you'll make sure that whatever is at the back, yes, whatever is, because you're storing in the decreasing fashion. So you check the first element, then the next element, and whatever is smaller, again, you can just keep a smaller than equal to, that is still okay. So you have to just remove all these smaller than or smaller than equal to elements, both will work. So remove all of them. So please make sure you remove all of them. So this will make sure it removes all elements that are smaller than your a of I or smaller than equal to. Once you have done that, the current index can be taken into your deque. And once you have done this, again, you know that you start taking your subarray maximums. In our example, we started taking from the second index because this was the last index of the first subarray. So you just make sure if k minus 1, because k was 3, so the first index was 2, if you remember. For k equal to 3, the first index where you started taking the maximum was this. So if it is greater than k minus 1, you simply take whatever is at the front and you say this is my maximum, and you store it in your answer, and at the end of the day you can return that answer. Now in the Java solution, you can see that you're given an array as well as you're given the sliding window size. So we compute the length of the array. We declare an R which stores all our maximums, and you know the number of subarrays will always be n minus k plus 1. Very simple. And now what we do is we store a right index. Basically what you have done is you have created the R array and you kept it Ri so that you can easily store answers. Nothing special. Right after that, you declare a deque. Once you have done that, you remember you iterated from the index 0, 1 till the index 7, and you used a pointer. So that is what you have declared, I equal to 0 till a dot length. Now what you are doing is, at the first, make sure you remove all out of index guys, out of bound. So if this was your array and you were standing at the index I, so you know this is the subarray which you're considering and the length is k. So anything beyond this, that is I minus k, right? This will be I minus k. So if your peak, if from the back, that is equivalent to I minus k, correct? If your peak, that is the front, if that is equivalent to I minus k, so it's an out of bound index, whichever is at the front. So just make sure you remove it, right? So you have removed it. And also make sure you check Q is non-empty, because it might happen the Q is empty and you're doing a peak, so it'll throw a runtime error. Right after that, you have to remove small elements. So just make sure the Q is non-empty, and right from the back, check if that element is lesser than. Again, lesser than equal to can be used, that is okay, and you can also remove anything. So this removes any element that is lesser than equal to a of I. Equal to can be removed, or you can write it, that is your wish. So I make sure remove all of them. Once I've removed all of them, I just make sure whatever is at the current index, I just take it and push it into the deque. Once I've done this, so if you remember, our first maximum that we took was from index 2, because this was the first subarray and k was 3. So the subarrays that we start as is from 2, 3, 4. So can I say any I that is greater than k minus 1? K was 3 and we started taking from 2. So I, whenever greater than k minus 1 is when we start taking. And we have kept an Ri. Initially that's 0. So we just do R of Ri plus plus and we take whatever is at the front, because that is the maximum element. So this is how a big O of n plus n, which is near about n solution, will look like in Java. So guys, I hope you have understood the entire explanation, entire intuition, the C++ as well as the Java code. Just in case you did, please make sure you like this video, and if you're new to our channel, do consider subscribing. With this, let's wrap up this video. Bye bye, take care.
Whenever your heart is broken.